In this project, my first step was to identify the type of modeling task. As the task was to predict the electrical energy output of a combined cycle power plant based on environmental readings, I recognized it as a regression problem. So I was thinking about the task as of a regression model where I need to predict a continuous output. I analyzed the features and saw that relative humidity has the least impact on the output. Nevertheless, I decided not to eliminate humidity and see how it works out. To explore the data, I chose linear regression and decision tree models to capture the underlying patterns in the data. I've built my models using Python and libraries such as Pandas, scikit-learn, and Matplotlib for visualization. I started with a linear regression model, like a classic choice for regression tasks. And later on, I also tried decision tree model because they are well known for their ability to figure out complex relationships, and I wanted to give it a try. I also used a validation set to fine-tune my decision tree model. I tried a few combinations of features and hyperparameter tuning. By comparing my two models, I wanted to find the one that would perform better on the validation set. After training my models and playing with the features to receive a better result, I decided that the models are ready for evaluation. I selected three metrics to check the accuracy of the predictions: mean absolute error, mean squared error, and R-squared. I took a separate testing dataset to check my models on it to be sure that models can work well on new unseen data. Here you can see the results for linear regression, and here is the result for tuned decision tree model. Now about the model interpretation. As we can see, our linear regression model performs pretty well. Mean absolute error has a value of 3.65, which represents the average absolute difference between the actual and predicted energy output. Practically, it means that our linear regression model's predictions are on average about 3.65 units away from the true values. Mean squared error of 22.2 quantifies the average squared difference between actual and predicted values. This metric shows us how well the model handles larger errors. R-squared measures the proportion of the variance in the target variable, energy output, that is predictable from the independent variables. In our case, 92% of the variability in energy output is explained by the model. Now let's have a look at our decision tree model. Here, our mean absolute error has a value of 2.9, which is definitely better than 3.65 of linear regression model. Mean squared error is 16.27, which in my opinion is very good compared to the linear regression model, which means that decision tree model is better handling of larger errors. And we have 0.94 in R-squared, which means that the decision tree model explains approximately 94% of the variance in the energy output. Overall, both models demonstrate strong predictive capabilities, but the decision tree model is showing slightly better performance. Both models capture patterns in the data and provide reasonably accurate predictions. Potential weaknesses could include overfitting, especially if we're talking about the decision trees, or limitations in capturing complex relationships present in the data.